Good afternoon, everybody. Thanks for joining us yet again for our Occupational and Environmental Health Seminar Series at UBC. It's my pleasure today to introduce Martin Stangl, who is a professional environmental / chemical / civil engineer with Rowan, Williams, Davies, and Irwin, otherwise known as RWDI. He's accredited in both British Columbia and Ontario. Martin's been with RWDI for 9 years now. He's a team leader and senior engineer in the exhaust re-entrainment group, specializing in wind modeling of air quality issues. Martin has worked on hundreds of projects involved in exhaust re-entrainment across all sectors globally, including several buildings at UBC, landmark projects such as the expansion to the Grand Mosque at Mecca, and projects as far north as Fairbanks, Alaska. We're very lucky to have him here with us today. Thank you, Martin.
Thank you, Sarah. So welcome, everyone. Thanks for coming out. I know you're joining us, some of you over part of your lunch hour here. Today I'm here to talk to you about physical air quality modeling using wind tunnels. So that's quite a mouthful, and we'll get going here. First, what I'm going to do is just give you a little bit, we got a little bit of background from Sarah here, so I'll skip over the slide quickly. I'll give you a little bit of context about where I'm from and who I work for. I graduated from the University of Waterloo. By training, I'm a chemical engineer, and like Sarah said, I work in the environmental civil arena, and I work a lot with air quality, and we're going to talk about what that means to me. Registered professional engineer, and I'm also a member of ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And that's important because I deal a lot with building systems, exhaust and air supply systems. The company that I work for, that I work with, is called Rowan, Williams, Davies, and Irwin, RWDI. And we're consultants. We consult with architects and mechanical, electrical, all manner of engineers in the science of buildings and the environment. We look at the performance of buildings, we look at the climatic response of buildings, and we look at the comfort of people who use buildings. The company was established in 1972 out of Guelph, Ontario. We've got over 350 people worldwide. We have offices right here in Vancouver at Oak and Broadway. Our main office is in Guelph, Ontario, which is near Toronto, if you've never heard of Guelph. And that's where we house 2 and soon to be 3 of our 4 wind tunnels that we have globally. The other one is in the UK. RWDI, I'm going to be talking to you about a very small slice of what RWDI does and what they consult on. As you can see here, obviously we're not going to go through all these, but we look at wind and wind effects on buildings and people. We look at ventilation in buildings, air quality. We look at sustainable design, noise and acoustics, vibration, sun, sand, basically all manner of things that have to do with buildings and people. We're going to look at a very small slice here. And like I said, we work with architects and engineers from very early stages where we're talking about conceptual type of designs. Where should we lay things out? How do we sort of consider this whole concept of air quality in the realm of mechanical engineering and architecture? Because every discipline really brings its own bias and its own ideas to the design process, and we really want to feed in there. And then, of course, you can provide consulting and design guidance as the design of buildings progresses, all the way into advanced detailed design. And you can see there's a picture of a red building there with some smoke coming out of it, and that's basically a building in one of our wind tunnels. So we get into proving the concepts and testing the types of recommendations that we might provide. Buildings are everywhere and people are everywhere, so this type of thing applies across all sectors. Healthcare is, of course, probably of most interest to you folks here, but we get into education, residential, airports, science and tech, basically anywhere people are using buildings. So just a little bit of an outline of what we're going to talk about. This is very brief. We'll get a bit more detailed. But we're going to define what is air quality in the context of what we want to talk about today. The term air quality is actually very broad, and we really want to focus in. And then I'm going to introduce you to this term exhaust re-entrainment. This is, you won't find this in the dictionary. This is an engineering term. There are a number of engineering terms that aren't found in any dictionary. So it's good to talk about what that means and why we care about it. We're going to talk about how we assess air quality, what are the tools and methods we can use. We're going to zoom right into using wind tunnels as our tool and find out what is a wind tunnel, how does it work, and what are the steps involved in doing this type of air quality study in a wind tunnel. And then at the end, we'll touch a little bit on other neat stuff you can do with wind tunnels, because that's sort of part of the goal today. So this is just an overview of what I mentioned here. We'll talk about what is air quality, what is exhaust re-entrainment, and why do we care about it. So when we talk about air quality, we can talk at a variety of scales. We can talk about large-scale transport, sort of regional transport on a scale of hundreds to 1,000 kilometers. We can zoom that right down into sort of state, city, right down to a building scale. And the building scale is really what we're interested in here. We're not really necessarily modeling what gets put up in the atmosphere and how it disperses across large distances. We're talking about acute, local, short distance transport of pollutants. We're talking about the stacks that are up on UBC chemistry and other buildings. And where does that stuff go once it comes out of the building? So when we talk about these buildings, and actually a campus like UBC and any kind of a diverse educational campus is a really good example. Normally we'll walk, we'll cycle, we'll drive down the streets, and we won't pay a whole lot of attention to those stacks and funny things sitting up on rooftops and the air supplies and things that hum all around us. But really, these are integral parts of the building systems. In a lot of our buildings, especially on school campuses, we're doing research where we're working with chemicals and fume hoods. We want to make sure we don't breathe those. So they go up the fume hood. After they go up the fume hood, where do they go? Well, they go out of a stack on top of the building. And then what I'm interested in, what happens after that? Where does it go then? Does it come right back into the building through a window? Or does it just drift up into the atmosphere? So a fume hood's just one example. We'll go through a few examples of sources of air pollution and odors. But this is an example of a hospital. You can clearly see that there's all kinds of stuff that we might want to consider. We might have a helicopter coming in and landing, burning some kind of fuel that we might smell. We have fume hoods. We have trucks and vehicles, ambulances that drive around. We have heating plants, cooling plants. All of these produce some sort of pollutant or odor that is emitted up into the air. And then it's important to know where it goes after that. So I'll just go through a few photos here just to make it a little bit more real than a caricature. On the left here, this is a loading dock. Most buildings have loading docks. They're tucked in the back where most of us don't see them. But essentially, we're taking deliveries, and often we've got large trucks, large diesel trucks backing in. And if anyone's ever smelled a diesel truck, you know kind of what the issue is here. And this on the left is actually a photo I took on my very first site meeting and site visit as a young engineer with RWDI. And it's actually a perfect example of what not to do. You can see those exhaust pipes coming from the top of that truck are pointing precisely into a window there, and I like to tell people that's a professor's office or something like this. I'm not exactly sure. A very common source of air pollution and air quality issues that I deal with on a daily basis is a diesel generator. A diesel generator is nothing more than a really big diesel engine that provides backup power if the grid goes offline. These things are tested on a regular basis. They have to exercise them to make sure they work. And if the power goes offline, they could run for extended periods. Now, these burn diesel, and diesel produces noxious pollutants. It produces nitrogen dioxide, which is problematic for the respiratory system. It produces particulate matter. Same thing, problematic for the respiratory system, carbon monoxide and other smaller level pollutants. It also produces a very strong smell. So you get into a situation where if you are on, say, a medical campus and you're burning diesel and somebody smells something, it may or may not be at concentrations that can be shown or proven to affect health, but there could be perceived health effects, and it could cause other issues that I'll talk about. Cooking odors is another one. That's a nuisance that we want to maybe try to avoid. Helicopters, I mentioned earlier, helicopters are very important. We're often quite limited in where designers can place a helipad because you want to be close, you want to get that patient in and get them to care as soon as possible. So that has to be balanced with where we place air supplies for buildings. This is an example where this building here was getting helicopter fumes sucked into the air supply, so they had to move those ducts. Those of you online can't see my pointer here, but that is if I can turn it on. There we are. So these ducts get moved up here to try to reduce the amount of these smells that come back into the building. Fume hoods, real common one. Any kind of a research building, chemistry building, even hospitals, There's fume hoods everywhere. We use anything from strongly smelling chemicals, toxic chemicals, odorless chemicals that may be toxic, powders, all kinds of stuff that we use in fume hoods that comes out the building. And we really need to, as engineers and designers, be conscious about where are we emitting the stuff that we're putting in the fume hoods when it comes outside the building. This is another classic example of what not to do. I think today we're a little bit more savvy and we don't do this kind of thing, but there are all kinds of existing buildings out there, all kinds of university college campuses, research buildings, whatnot, where you'll find this type of thing with stacks and caps on them and real short, close to air supplies. We've kind of covered up this fellow's face here, but he actually has to wear a gas mask when he goes up and visits this roof. And this is a real building that one of my colleagues was on, and he took this photo. Cooling towers. I don't know if everyone here knows what a cooling tower is, but essentially what we're trying to do is we're providing cooling for a building. We're cooling processed water, whatnot. And what happens in a warm, moist environment? Bacteria grows. And in cooling towers, there's a bacteria called Legionella, causes an ailment called Legionellosis. And this can be really problematic for people with respiratory ailments, particularly the elderly. And there have been cases in Canada where there have been Legionella outbreaks that have actually caused deaths. Usually it's at senior center, senior care homes where, again, people have compromised immune systems already. So what we do with cooling towers, to avoid the growth of that bacteria, we treat the water with chemicals. Well, when we treat the water with chemicals, chemicals can evaporate into that big white plume that you see and carry all over the place. So we're really concerned about where we place these. So I've kind of touched on this a little bit. I've given a few examples, but this is a good time to introduce this term exhaust re-entrainment. So all this means is the re-entry of pollutants and fumes that we've emitted outside into a building. It can be back into your own building. It can be a neighbor's building. It can be down to, say, a daycare or a play area down at grade. It doesn't really matter. The whole idea is we tried to get it out. We don't want it coming back in. And what's really important with exhaust re-entrainment is usually these plumes, these exhaust plumes coming out of these stacks, you can't see them, just like you can't see the wind. And so it's important to understand the wind and what it's going to do. This is a really neat example. You wouldn't expect, this is sort of some full-scale testing we did some years ago. These are fume hood exhaust. You wouldn't actually expect this plume to come and curl down to those people, those nice people that are sitting and standing there in the corner. This is not something that's intuitive, but it's something that we need to understand and know in the design process so we can avoid this type of situation. So I got a little bit ahead of myself here, but these are just some visual examples of what I mean by cross-contamination, self-contamination. We can contaminate our own building, or we can contaminate a neighbor or any kind of air-sensitive spot. Just another example of that very thing. One situation, as soon as you start putting buildings in the mix and structures in the mix, things get complicated. And when we're in urban centers or heavily built up education campuses, this becomes an issue when you have some buildings that are taller, some that are shorter. The aerodynamics change, and we start to get a whole lot of what I call receptors, air-sensitive receptors, places that are sensitive to the air quality, and we really have to be conscious about how we design for those. Understanding of the wind is really key. If we take a single building or a block or a structure in isolation, really what's happening is the wind, it's moving along, it's traveling along, and it intercepts the structure. So what is it going to do? Where is it going to go? Well, it's not just going to stop. It's basically a blunt face, and it's going to push the wind around. Some's going to curl down, some's going to curl over and over the roof, on top of the roof. And what happens on a rooftop, and you can see it in the photo on the top right there, is what's created is something called a wake zone. And you can visualize this as a bubble on top of the roof. There's a bit of a negative pressure zone inside that bubble, and it's because the wind over top of that is accelerated over that curve. And it'll create a bubble because eventually it'll come down because it wants to rejoin the free stream of the wind. And these wake zones and these bubbles are important because if we're emitting some kind of pollutant or odor or something in a negative pressure zone, what's going to happen? It's going to tend to sit there and stay there and contaminate any kind of air supply that's already there. So again, wind flow around buildings is really important to understand, and that's really what I deal with every day. Air quality is sort of a subset, very related to understanding of wind flows, and these are some examples, as I mentioned. So fine, so we've defined a few terms. We're talking about air quality, local air quality on buildings. Are we going to affect ourselves, neighbors? Are we going to create a good environment for patients? Well, why do we really care about this stuff? I mean, we've got it out of the building, fine, great, it's going to disperse and dilute in the atmosphere. So why is it really an issue? Why are there people like me who look at this? Well, the issue is that there's still health risks. Health risks are not only associated with breathing pure chemical in the fume hood, it's not only associated with that real close exposure. The concentrations of whatever we're emitting could still be high enough after they've dispersed a little bit in the environment, after they come back in the building, to cause short-term and long-term health effects. Again, it totally depends on what it is that we're using, but it's important to consider. Nuisance odors. This is another big issue here. Okay, we might smell the hamburgers down the street. It may or may not bother people, but again, once we're in a healthcare environment and we're dealing with people who are trying to heal, who have compromised immune systems, who are extra sensitive to any kind of smell, we really don't want any odors coming back in the building, regardless of whether we might think that they're pleasant in another environment. This means diesel, this means cooking, this means chemical odors. And generally speaking, when we're talking about buildings, I don't know, has anyone heard of sick building syndrome? So I see a lot of heads nodding yes. So again, we're pulling in bad air, air that's not clean, air that's not fresh into buildings. And this can lead to decreased productivity, in hospitals, poor patient experience, in extreme cases, complaints, work stoppages, in very extreme cases, lawsuits. And at the end of the day, usually when we have poorly designed stacks, it's related to greater energy use. We need more energy to pump that out, and I'll talk about that a little bit later. So what do we do about this? So now that we have an understanding that these issues are out there, we're designing buildings, we have sources of air pollution, these stacks on the roof or at grade or wherever we put them, we have air supplies and we're worried about the people inside, what do we do? So the first thing we can do is ignore it. We can do nothing. But in this day and age, that's not really an option. Usually I like to show this slide because I really enjoy that photo, but as a consultant and an engineer, the first thing we can do is we can offer our experience. And what you'll find in this industry, if somebody's looking for this type of a service where we're looking at the air quality and the dispersion and the re-entrainment airflows around buildings, you can do some experience-based consultation. Early in a design process, you might get team members, architects, engineers, other consultants sitting around a table. Today it's called an integrated design process. And there's an exchange of ideas. And this experience-based consulting is part of that process. It's an exchange of ideas and experience to try to get at least the concept and the basic building design to a point where it can move forward smoothly. Beyond that, once we get into detailed design, or if we want to dig a little bit deeper, we do modeling. And normally, sources of air pollution and air quality, normally they require permits and there's some sort of modeling that's required. And usually that modeling is based on spreadsheet, empirical, analytical models that are basically under this category of computer modeling. And much of it's based on dispersion of plumes, how plumes disperse. Many of those models are based, at least in part, on something called a Gaussian plume dispersion model. It basically tells you how a plume spreads and moves as it comes from that stack and where it's going to go under the influence of wind. But the other thing we can do is physical modeling. Instead of sitting at our computer and working through equations to try and predict what's going to happen, we can build a physical model of our building, of the buildings around us, of the site, of the exhaust source, the pollutant source that we're worried about. We can include the air-sensitive receptors that we're worried about. And we blow wind at it, and we see what happens. Physical modeling, otherwise known as wind tunnel modeling, is actually it is the most accurate and the most robust tool available today to do these types of studies. At the end of the day, it is still also based on where is that plume going to go. We still need an understanding of how it spreads, where it goes, but what we're doing is we're doing it physically instead of with computers. So let's dig a little bit deeper into that. I'm going to go over wind tunnels and how they work. I'm going to show you what is a wind tunnel, what does it look like, and what are the steps involved in doing one of these types of studies. How do we actually assess air quality using wind tunnels? That was the title of the presentation. And then how do we use the data that comes out of it? It's great that we can collect some data, but what good is it if we can't understand it, we can't do something with it? So we're going to go over what we do with it. So in a wind tunnel, the first thing we need to do is we need to simulate the wind. And on the surface, you might think, what's so complicated about that? We'll turn on a fan, we'll blow some wind, and there we go. But it is a little bit more complicated than that, because what we're trying to do is we're trying to simulate wind as it blows across the Earth's surface. It's a fairly large-scale phenomenon. And as you know, the Earth isn't smooth, it's rough. We put up buildings, there's trees, there's all manner of things that create a rough surface. And as with any fluid that flows across the surface, as the roughness increases, what you get is a profile, a wind speed profile, or a fluid speed profile. In this case, we're dealing with wind. So in this image, what you can see on the left, we're talking about an urban city core. In the middle, we're talking about more of a suburban type of setup. And on the far right side, we're talking about sort of open land. And what you can immediately see, if you look closest to the ground, the wind speeds close to the ground are fastest in the open terrain. Again, anyone that's been to the prairies can probably attest to how fast the winds whip around there. As you rise in elevation, what happens is the winds start to get faster, because what's happening is you're getting further from the influence of this friction of the Earth. Eventually there's going to be a height at which the wind speeds are no longer affected by the friction of the Earth, and that's called gradient height. Here it's showing it at 500 meters. For practical purposes, for the studies that I do, we call gradient height 600 meters. And the advantage of knowing that height, and I won't get into it here, but it's that we can start translating wind speeds and correlating wind speeds from one environment, from an open environment, say from data collected at an airport, to our actual site, which may be urban or suburban in nature. There's various types of wind tunnels, but basically, I know I said it was more complicated than just blowing air through a fan, but that blowing air through a fan is a critical part of this whole thing. This is an example of one type of wind tunnel that we have built in Guelph. The photo is actually a photo of that tunnel. This is more of a straight wind tunnel. You've got a fan at one end, the left end here. It goes through an expansion and a contraction section, and it blows into what we call the study section there. It blows across these blocks, which I'll explain in a moment, and then it blows across the study model. And what you'll notice is that it's on a circular disc, and we can turn it so that we can evaluate winds from different directions. And the fan is a variable speed fan, so we can evaluate different wind speeds. Another type of wind tunnel, and this is the type that I work in most often, similar concept, this is called a recirculating wind tunnel. And what you'll see is on the bottom of this image, with all those little squares and the big circle there, that's called the test section. So what happens is on the top part, where you see the fans, right up here, that's where the fans are actually creating the pressure and blowing the air. And on the right side, we basically have these turning vanes, so the wind is turning around, basically pressurizing that chamber, and then coming through a set of straighteners here, flow straighteners. You can't really see them, but it's this blackness behind those spires. That's where the straighteners are. The wind comes out there, hits those spires, and I'll explain what those are for in a minute, comes across this roughly 45-foot test section, and then blows across the study model. And then after it blows across the study model, it turns again at the end, after that big circle on the left side here, back into the fan section, gets picked up again and blown around. So it's just recirculating over and over and over again. So one thing I mentioned earlier was this idea of a wind speed and wind speed profile. The other thing that's really important when we're talking about wind is turbulence. So who here has taken fluid mechanics? Has anyone taken fluid mechanics? We've got one hand up from the engineer over there, okay. Well, basically, when we talk about fluids, fluids generally, unless they're at very slow speed or we're talking about very low friction environments, they're not just floating along. They're moving, there's turbulent eddies. I don't know if there's any canoeists or people that like to ride on rivers in the audience, but you've probably heard the term eddy. There's small pockets of wind that are moving in all directions. The bulk of the wind, if you look at it as a bulk, it's moving in one direction. But within that, we've got wind moving left, right, up, down, all over the place. So we need to also simulate that turbulence and that turbulence profile, vertically and laterally. So these spires that are at the back, they actually create the turbulence. So the wind comes around these turning vanes, it gets straightened, and it hits these triangular spires, and it trips up the flow, so it's moving around, and we create those turbulent eddies. And then it comes across these roughness elements, and these are what simulate that wind speed profile. So on this particular image, the blocks are very small, so we're simulating an open environment, some open fields, farmers' fields, things like this. If the blocks were bigger, we might be simulating a suburban environment with homes and low-rise apartment buildings. And if they're really big, we would be simulating a downtown urban core. So once we've figured out what we're going to do with our wind, we've figured out our wind speed and our turbulence profiles. Wonderful. What we have to do next is we have to build a study model. So most of the time, or a lot of the time, I would say, we're dealing with new construction, concept designs, things that are only on paper, so we have to turn this into reality. So what we'll do, usually we're working at scales of 200, 300, and 400 times smaller than the real thing. We've got a full-service model shop that actually builds these models. There's all manner of models being built at any one time in the shop. This is an example of it's the University of Texas Experimental Science Building. This is a study that we did for this very thing, air quality in a wind tunnel. Once we've built the actual shell of the model, what we have to do is we have to instrument it with the stacks and receptors. So in the real world, you might have a laboratory stack. It might be 15 feet high, a foot in diameter. Obviously, we can't build that in a wind tunnel, so we scale it down. And there's scaling principles out there that are published that we use to estimate how big these stacks need to be. We install these where they need to be installed, which is basically where they would be on the full scale, but at small scale. And you'll see in the bottom left here on 2C, there's a whole bunch of tubes coming out of that building. What we're doing is we're installing receptors. And what those are essentially just sampling points for the study, and I'll explain to you how that works in a moment. Once we've got that study building built, of course, we need to build the surrounding buildings, at least the massing, to basically simulate what are the wind flow patterns in and around our building. Generally, the local turbulence and wind flows are what influence small stacks on buildings, so it's quite important to get those fairly accurate. Then we install in our wind tunnel. So what you saw in earlier photos was the nice top view. You've got a model sitting on a big circle that can turn. You've got the test section, the section where we blow the wind in. But there's a lot that actually goes on under the wind tunnel because there's all kinds of tubes that deliver tracer gas, the gas that we're going to use to sample, and tubes that come down and sample that gas that are connected to those receptors that I talked about earlier. So there's all kinds of equipment under that wind tunnel that are all involved in that sampling. And here's the final product. I know we've seen a few of these photos, but it gives you a sense of the size of these stacks, that exhaust and receptor ports that we're dealing with on a model scale relative to the building scale. They're fairly small. So the way an actual test or analysis works here, once we've built the building, is we have these stacks, and what we're trying to do is we're trying to simulate what it is that comes out of here. In a wind tunnel, we're not actually concerned about what the specific pollutant is when we're running the study, because there's just too many to deal with. What we're doing is we put in what's called a tracer gas, and this is just a gas that we can emit and that we can measure a concentration of. And what we can do is we can apply scaling practices later on to understand how the results relate to actual pollutants. So we're emitting a tracer gas of known concentration into this wind tunnel. We're blowing wind at the model. We're turning the model. And what we're doing is at these receptor points, you see point number 4 there, we're taking a sample. So this is a tube under draw, and it's sampling the air around it. So if this tracer gas that we've emitted from the stack travels towards or makes it anywhere near this receptor, based on the wind flow patterns that are created around the buildings, it's going to take a sample. So if we know the concentration that's coming out of the stack, and we can measure that's the concentration that's coming into this receptor, we know what the relative concentration is. Or another way to say that is we know how much the exhaust has been diluted by the time it gets to the sampling point. And if we know this dilution ratio or concentration ratio, we can bring that back to the real world and apply any kind of full-scale concentration of nitrogen oxides, particulate matter, whatever we know is coming out of our full-scale source. We can apply this dilution factor and know what the concentration of that particular pollutant or odor is at our building. And once we know that, we can make a judgment as to whether it's safe, whether it's going to be a nuisance, whether it's okay, whether it's not okay. So this is what a data set looks like. I mentioned that what we do is we can spin the model, we can measure a variety of wind directions, and we can measure a variety of wind speeds. Well, this is essentially a matrix. I'm sure you've seen this type of thing in math class, even all the way back to high school. Across the top, we have the different wind directions that we've sampled. It's our x-axis. On the y-axis, on the left there, we see the different wind speeds that we sampled. And you can see these are in 1, 2, 3, 4, 5, 6, 8 rows here. And each row or collection, each bulk row here is one of these receptor locations. So one of the sampling points. Okay? So we know for each sampling point, for essentially any combination of wind speed and wind direction, what's happening there. How much has the exhaust source been diluted by the time it reaches that receptor for that particular wind speed and wind direction. So what you're seeing here are actually dilution ratios. 900 to 1, 1,000 to 1. 1,000 to 1 means that it's been diluted 1,000 times. So we've got a set of data. We've got dilution ratios. So what do we do with it? I alluded to this earlier, but one thing we can do is once we've taken those factors and applied them to the actual pollutants and stuff that we're emitting that we're concerned with, we can compare them to safety criteria. Depending on the type, the venue that we're dealing with, the types of people that we're dealing with, we can apply occupational health standards, air quality exposure limits. We can apply ambient air quality standards that apply to the general population. We can also apply emergency response standards, something like an IDLH, which means immediately dangerous to life and health. Normally we want to stay away from something like that, and we want to design to meet ambient air quality standards and occupational air quality standards, because with those standards we're dealing with, yes, we're dealing with concentrations that could be harmful to some degree, or irritants, say, respiratory irritants, but we're not talking about something that's going to make people keel over. We want to stay far away from that. We can also look at odors. Again, I mentioned earlier that odors are really important because not only can they be a nuisance, but an odor can also be interpreted as a perceived health effect, especially when we're talking about a healthcare and healing type environment. But odors are very complex. The perception and detection of odors changes from person to person. I may be able to smell something that you folks in the audience cannot, or vice versa. My nose might be more or less sensitive than other people's. And a certain type of smell, which may be pleasant to me, may be offensive to somebody else. So it gets very complicated. So how do we figure out what is an appropriate level of odor? Well, it's essentially impossible to try to design to eliminate all odors or to make sure it's okay for every single person. So what we deal with are odor thresholds. And normally the target odor threshold is a value, a concentration, that is called, and I haven't written it here, but it's also called a 50% detection threshold. It means that statistically, if you expose a population to this odor, 50% of that population won't detect a thing. They'll have no idea that there's a smell there. Within the other 50% of the population that will detect that odor, some of them will be able to detect an odor but won't be able to identify it, so they won't object to it either. A smaller portion will object to that odor. They'll have particularly sensitive noses. And the other ones in the middle may be able to detect it, recognize it, but may not object to it. So we're basically trying to make it okay for most people, if I can say it in the simplest way possible. So the places where we get odor thresholds, they're either published for a variety of chemicals and compounds, common chemicals and compounds in various literature. If they're not published, we have to figure them out. And what we do is we conduct odor panel tests. What's involved in an odor panel test is essentially taking a sample of the odor in an inert, it's called a Tedlar bag, so we take a sample of this. It can be from a diesel truck exhaust, it can be from a kitchen, it can be from a wastewater treatment plant, wherever. And then we bring it back to a lab, and what we can do from that bag that has the pure sample in it, we can dilute it by various amounts. And then we get panelists, usually students who are looking to make a buck, in to come smell this stuff. And what they'll do is the person administering the test will release a small sample of the odor diluted by a certain amount that the person doing the sampling, they have no idea. They'll release it into the odor panel, and the person doing the sniffing has to tell you if they've detected something, if they can recognize the smell, if they object to it. So through this, you can basically create, if you sample enough people, you can create a statistical curve, And from that statistical curve, you can figure out where that 50% mark is, and that would be called your odor threshold. Just to give you a sense of the types of, we've been talking about dilution ratios, how much exhaust has to be diluted before it reaches an air supply or sensitive location to be okay, to be healthy, to reduce the smell to an acceptable level. But how much dilution does that actually take? And the answer is that it totally depends on the source that you're dealing with. These are just some common dilution ratios, so the amount that has to be diluted, that we deal with for different types of sources. The first one, very common source, a laboratory fume hood, 3,000 to 1. We have to dilute an emission 3,000 times before it comes back into an air supply. That's a pretty big number. The reason is, as you can imagine, in a fume hood, there could be any number of chemicals used. And the chemicals and compounds that we use today may not be the chemicals and compounds that we use 5 years from now, 10 years from now. So we have to design to be flexible. So this 3,000 to 1 is a number that we've used. It seems to be a practical target. Designers can achieve it. And it covers roughly 90% of chemicals on a list of about 400 commonly used chemicals that we've developed, chemicals that are commonly used in research labs. But of course, there could be many other chemicals that are used. Fume hood exhausts may need to be designed to a stricter target. If it's a fairly benign type of operation, you may be able to design to a less strict target. For combustion sources, combustion just meaning things that burn fuel, boilers, diesel generators, and trucks, these are some of the more common ones. We're dealing with criteria, health criteria in the hundreds, so diluted 100, 200, 300, 400 times, a little bit easier in some situations to achieve. And for odors, so again, people that have smelled a diesel truck, you probably know it's a fairly strong odor. Well, a diesel generator, just being a really, really big diesel engine, produces a lot more of that diesel odor. And generally speaking, to reduce a diesel odor to what we would call a generally acceptable level takes a dilution ratio of 4,000 times. Real hard to achieve. Diesel generators are really, they can really be a source of complaint and problem in a lot of places. And often designers are limited in where they can put them because they're big and they're heavy and they vibrate. So designers may or may not want to put them on a roof. They have to reinforce the roof, put in vibration controls. It might be expensive. They may want to put it at grade. If they put it at grade, it might be close to windows. So we might say, well, put it real far from the building. Well, if you put it real far from the building, it's expensive to run the lines back to the building. So achieving 4,000 to 1 within the constraints of a typical design when we're talking about practicality and cost can be difficult. So that's where these types of studies really do come in handy. Cooling towers we mentioned, we talked about this whole idea of Legionella and how we treat the water with chemicals to avoid the growth of this Legionella. The chemicals that we're using in there, at least the evaporative emissions, they're not that significant. We only need a dilution of about 10 to 1. The problem is the volume of exhaust that these cooling towers produce is enormous, on the order of hundreds of thousands of cubic feet per minute. That's a lot. A typical laboratory fume hood exhaust will produce between 1,000 and 20,000 cubic feet per minute, not 300,000 or 400,000. So when you have that much stuff, it's very hard for the environment to disperse it. So so let's say we're talking about a dilution ratio of 2 to 1. The atmosphere has to basically dilute that with an extra volume of clean air to get to that 2 to 1. So you can imagine if we have 400,000 CFM of plume, you have to dump in another 400,000 CFM of clean air. The atmosphere has to do that work to get it diluted by an extra factor. So it does definitely become difficult. And kitchens, again, cooking odors. Odors are the most difficult to design for. You need 600 to 1, which again can be difficult. I can smell the Vietnamese restaurant that's probably 50 or 75 feet away from our front door of our office on the days that the wind blows in the right direction. So tells me when lunch is. So the other thing we can do, if we know now that we've got a data set, we understand for different combinations of wind speeds and wind direction what might happen. We've compared to some criteria. Let's say we've got a source we've compared to an occupational health criteria, and we're not meeting it. The concentration's too high. Well, what do? To understand how significant of a risk it's going to be, we need to understand how often it might happen. And because we've run these wind tunnel tests, I think it's important to collect that wind data and understand how often those winds happen. So if, for example, we have a south wind at receptor 7 there in the top, a mid wind speed, we've got a fairly low dilution. You can see from this windrose, this is a Vancouver windrose. East and west winds are most common, south winds are less common, so we may or may not be very concerned about it. It's an important factor. So once we know what is the risk, how often might it happen, if we've determined that there is a risk and we want to fix it, there's different types of things that we can do, and we can use the wind tunnel to evaluate. One is making those stacks taller. I'm close to the University of Guelph. The University of Guelph has a lot of real tall stacks. Just driving around the campus here, you guys have the same type of thing. The reason for those real tall stacks is to get them up and out of the influence of these rooftop wake zones that we talked about earlier, up into the atmosphere so they can disperse properly, so they're less affected by the turbulence and the wind effects of the building. We can move the stack. If we've put it in a spot that's not really practical, that's not really great from an air quality perspective, maybe on a low roof close to an air supply and or open window, we can move it. The challenge from a designer's point of view is that only really becomes practical early in the design process. It can be done late in the design process, but it becomes more expensive and more of a pain. We can increase the speed, the velocity from the stack. We can increase the speed that the effluent comes out of the stack. You can imagine we might get more plume rise. What's coming out of there is going to shoot higher into the atmosphere and basically, hopefully, help to get us, again, away and out of those wake zones that we're really worried about. Usually this is only effective when you're starting with a low velocity. You know, more and more the designers that we're running into, they're more and more savvy, and they're already designing these stacks with high velocities. The downside to a high velocity is it costs energy. And energy is, again, something that everyone is very, very interested in nowadays. So speaking of energy, one thing we can use wind tunnels for is to evaluate these types of air quality issues. And by evaluating them and understanding what's going to happen, where our impacts are, and for what kind of design, we can use that knowledge and information to save energy. And the way to do it is by modifying our exhaust designs and or our air supply locations and window locations to minimize contamination while at the same time that we're trying to reduce flows. As an example, I'm going to use a lab as an example. During occupied mode, you may have a number of researchers or students using a lot of fume hoods, and the fan that is basically pulling the air from the fume hoods and dispersing it out into the atmosphere outside is running full tilt. Makes sense. But in the evening, we may have an unoccupied mode. Sash is down, nobody there, minimal flow rate through the stacks. So do we still have to pump all that airflow and use all that energy that we were using during occupied mode? If we've got a contamination issue that's been shown through the wind tunnel tests, yeah, maybe we do. But maybe we don't. Maybe we want to show that we can actually pull that flow rate down, use less energy, use less air. And when you use less air, what happens? Your exit speed from that stack comes down. We're no longer necessarily able to escape these wake regions on the roof, and you increase your possibility for contamination. Well, that's something we want to avoid. So either we want to prove with a test, a wind tunnel evaluation, that it is safe to reduce those airflows, or we need to come up with other strategies to be able to reduce those airflows. As you can see from the graphs here, these are just some examples. The potential energy savings here is significant. Fans use a lot of energy, and we want to find anything we can to reduce that energy consumption. So there's 4 basic types of ways we can do it. One is the normal way. We've designed our stack, we've done a good job, it works, we can turn it down, everything's safe, great, we can save energy that way. If it's not safe, one thing we can do is we can use something called bypass air. So usually what that means is you have a fan with a damper, and when you turn down the demand from the building, air is pulled in at the roof to keep that one big fan going at a high rate. And so whatever we've put in through the fume hoods is still being diluted and pushed out by a nominal airflow at the fan. So there's one thing to have a bunch of small fume hoods connected together, but what you're really interested in is what is that total airflow rate at the fan. If we find that we do have an issue or we can't bring in bypass air, one thing we can do, as I mentioned earlier, is just make tall stacks. We can't turn it down, let's make the stack taller. We automatically get it out of those wake zones. If we turn the flow rate down, velocity reduces, but it's still high enough to be out of those zones because the stack physically is out of those zones. Another way we can do it is we can use that wind analysis. We can look at probability. Let's say we've determined that there is a potential for contamination but it's only for a certain section of winds that happen, I don't know, 20% of the time. Well, we can set up an active system on the roof with an anemometer, which is something that measures wind speed and direction, to basically tell us, or tell an operator, when those good winds and when those bad winds are happening. When the bad winds happen, we turn it up, we get that velocity. When good winds are happening, when there's less chance of contamination, we can turn it down and save energy. The challenge there is that it's expensive and it's complicated. Another way you can do this is called powered bypass. So instead of just bringing extra air into a real big fan, what you do is you have two smaller fans. One that runs in normal mode. You know what I'm going to do? I'm going to flip to this. One that runs in normal mode. And when the demand from the building decreases, what you do is you have this bypass fan, often called a slave fan. And it can be small. And what it starts to do is it starts to power up, and it provides air into that stack while you're reducing the demand from the building. So you're still maintaining that air from the top of your flue. You're maintaining your momentum. You're maintaining the airflow from that flue. You're maintaining the plume rise from that flue. So there's a variety of ways you can do this, but the whole idea is to be able to save energy safely during times that we don't need so much demand from the building. So wind tunnel studies, I mean, you may have put two and two together here. They're not exactly necessarily the most straightforward things to do. A computer model, we have set up equations, we can run them on our spreadsheets, but they may or may not be accurate. They're probably conservative. A wind tunnel study is less conservative. So when would we actually use a wind tunnel study? When does it make sense to go to this level of complexity and robustness? Well, usually when we're dealing with complex environments. We have complex buildings, complex surroundings, tall buildings, short buildings, strange shapes, and short stacks on those buildings when they're really affected by the odd turbulent effects and odd wind effects of buildings. You can really get interesting and funny things happening. You can get wind traveling in the complete opposite direction that you might expect. And the wind tunnel is the thing that's going to resolve all those issues for you. When we have receptors located near the exhausts, when there's a high chance for contamination, this is a time when I think it's important to use. The wind tunnel is less conservative than numerical models, and when we're talking to designers who are very interested in cost, we really want to take as much conservatism out as possible. Same thing, if we have receptors elevated compared to the exhaust, it means our air-sensitive receptor is higher. This is a very challenging situation to deal with. Again, numerical models can be conservative, and we want to keep their conservatism down. So that's kind of the summary of, the quick summary, I know it wasn't that quick, of using wind tunnels to study air quality. I've just got this one last slide here for you. I know we're a couple of minutes over time here, just to highlight some of the other neat things you can do in wind tunnels, other than putting cars and airplanes and things like this in them. Not that that's not really neat. But from a building and people perspective, what we can do is we can look at pedestrian comfort and safety. There are certain cities, for example, where they've built a lot of buildings and put them real close to one another, and it squeezes the wind through those buildings, so it can create very, very windy corridors and environments. The wind can be so strong that it can even blow people over. There can be situations where you can get wind rushing down the building and sucking doors open or holding them closed. I've actually had situations like that, and you can study those as well. Those are the extreme cases. You may also be interested in what is the comfort level of people using a space. You've got an architect designed a nice public space for someone to be able to sit on the bench, maybe read a newspaper. Is it going to be too windy? Is that newspaper going to blow out of their hand? Or say in a real hot climate, maybe it's not very windy, but we want some wind to create some comfort, so it's not stifling hot all the time. We might want to create urban environments where we encourage airflow. So there's all kinds of things we can do there. For tall buildings, we might want to look at what are the wind forces on that building, what are the wind forces on the cladding, which is basically the skin on the outside of that building. For designers, there are codes that they go by. Cladding is very, very expensive. Let's say you have a 100-story tall tower, all that glass that you put on that building is not cheap. If we can run a wind tunnel study to prove that they don't need to design it to such a high level as code might demand, they can save millions of dollars. These are not small dollars. Structural motions, bridges. Has anyone seen that video of the Tacoma Narrows Bridge breaking itself apart? That's wind-induced. So our company does a lot of work on bridges as well. and helipad operation. Again, buildings intercepting winds can create a lot of turbulence, and that can be dangerous for helicopter landings. And again, we're fairly limited in where we can land helicopters, and we want to make sure that we understand the wind flows that might affect that safety. So that's essentially it. Thank you very much. I know I'm a few minutes over, and the floor is open for any questions.
Thanks, Martin. I'm just going to pass the mic around the room to make it easier.
Sure. Are you going to pick who gets the first question?
Yes.
All right.
Hi there. Thanks for that. That was good. A lot of the stuff you touched on is like extremely relevant to our program. So I was just wondering, like, do you guys have any industrial hygienists working in the company, or do you contract them out, or?
Depends how much work we have. Yes, we do. I believe we do anyway. At least we used to. But we do get into that a little bit. Industrial hygiene is real important because it really helps us with our understanding of what really are the health effects of some of these pollutants that we're dealing with, particularly in an occupational setting.
Thank you.
Yeah, that was a fascinating talk. Thank you very much. I have two questions. One is, why would you ever not recommend a taller stack? Seems like the right thing to do.
Mm-hmm.
And then, second of all, I was just wondering about scaling effects for your model, your wind tunnel model to the outside world. What are issues that occur? I mean, I know there must be just assumptions of
Sure.
travel, but I wondered if there are any other sort of unusual scaling effects that are hard to account for.
Okay, well, to address your first question, why would we not always recommend taller stacks? Well, we might, but I guess the point is that we're consultants, which means we're providing a recommendation, and we have to balance this idea of practicality as well and cost. So there's practicality, cost, and aesthetics. Most of the time, we don't want our buildings to be ugly. As an engineer, I may not care, but an architect may care very deeply, and an owner may care very deeply. So there are usually a few different ways we can achieve the same solution, and a tall stack may not always be one of them. And then the question is, how tall is too tall? Right? I mean, we can always make it taller and taller and taller and reduce the contamination, keep reducing the contamination, but there are consequences to that as well. If you have a one-story building, you probably don't want a two-story stack. I know that's an extreme example, but that can happen. So it's a real balance when we're out dealing with people who are paying the bill and people who have to support the stack and whatever else. So we work within that integrated design process to come up with the best solution for everyone, while making sure that we're achieving a reasonable level of safety. To address your second question, yes, there are a number of assumptions. The scaling practices are based on established procedures, but of course there are limitations to the wind tunnel model, just like there are with any model. One important one is atmospheric stability. In a wind tunnel, you can only model neutral atmospheric stability. You can't model stable or unstable. And that's something that some of the numerical models can do, but of course they have potentially other shortcomings. The other thing is, the wind tunnel, like any model, it is a model. So what we're trying to do is simulate the real world. The real world is very, very dynamic. So what we're really trying to achieve is not to tell you what exactly is going to happen on November 3rd next year. We're trying to target a worst case scenario. What could happen under the worst case? And that's why we simulate a range of wind speeds and wind directions and conditions, so that we know, well, what could happen if the right wind came along, if the right stuff was emitted, and people were around. And usually, as a designer, that's where we go. That's a reasonably conservative approach that makes sure we're being reasonably protective of our population.
Thank you. I had two questions too, but she asked one of my questions about the toast. So my second question is, when you do your physical modeling, you're looking at what's coming out of the stacks.
Yes.
And getting back into the building at some point. But what about the other buildings around? What comes out of them? You look at how they also come into your building.
Absolutely. That's a very good question. Just to summarize, the question was, I talked a lot in my presentation about looking at what's coming out of our building, we'll call it the study building, and how it might affect our building and the neighbor's building. But what about what's coming out of the neighbor's building? Equally important, especially when we're in a design process to try to determine where we want to put the fresh air supply for a building. We have to consider not only what we are designing, but what's already existing around us. And that's where it gets real challenging, is we really have to work within the confines of our existing environment. And a new owner may not be able to put the onus of the liability on an existing facility to move or adjust its sources of air contamination to be able to be more flexible to place their own. So very, very well made point, and that can be a real challenge in design. That definitely needs to be considered.
Online question here, and it is, can you use wind tunnel modeling to study the dispersion and transmission and controls of microbes like viruses and bacteria in healthcare settings?
Mm-hmm. Well, what we use wind tunnel modeling for is to track and trace where that plume will go and how much it dilutes. So if that exhaust plume or that air is carrying, say, a microbe or something, or let's say it's even a virus that's attached to a particle, yes, if we know where the plume is going to go and where it's going to end up, we can predict where those microbes or whatever's being carried by that airstream will end up. There are probably other factors, like what about UV, what are other things that affect those microbes, but you can absolutely deal with that. The other thing that we actually model sometimes that you can use this type of tool for is radioactive emissions. So where do those radioactive particles end up? And then when you start putting these results together with half-lives and how long it takes them to decay, you can understand what a dose might be to a population at a particular receptor over the course of a year, and whether that's acceptable or not. So basically looking at cyclotrons and similar type of equipment.
Thank you for your presentation. I have a question regarding doing some of the works on newer buildings, because I know that in newer buildings they're trying to get natural ventilation in
Yes.
different buildings, and I'm just wondering if the wind tunnel setup could actually simulate whether the exhaust would also interfere with natural ventilation.
Mm-hmm. Good question. The question was whether the wind tunnel can simulate the effects of natural ventilation and whether the exhaust would interfere with natural ventilation. The easiest answer is we would treat a natural ventilation opening the same way that we would treat any other air-sensitive receptor. It's a way for air to get in the building. So the short answer is yes, we can deal with it. Whether the exhaust plume actually interferes with the functioning and performance of the natural ventilation, you can analyze that, but what you'd have to do is bring in other tools like computer fluid dynamics CFD to supplement those results, and those two tools could be used in conjunction to basically figure out how you think that system is going to perform.
Thanks for that. I was just wondering if you found, or if your model can account for climate and seasonal temperatures, and if that's a big factor in like your wind tunnel modeling, especially in places that are really hot in the summer and really cold in the winter.
To a degree, the wind tunnel model can account for temperatures. What you're really interested in is the density difference between the exhaust and the emitter and the local environment. Unless it's extreme, we usually won't go into it. Again, because the wind tunnel can only model neutral atmospheric stability, there are limitations. And when you get into extreme climate situations, you could also get into different stability classes, and you might want to supplement it with a numerical model. Again, we could supplement any kind of results from this with some sort of computer fluid dynamics model. But we have to be a little bit careful when we're talking about bulk airflows like this and re-entrainment and creation of wakes and things on buildings that would affect the re-entrainment, because the CFD isn't quite there. It can do a lot for us in terms of understanding the general wind flow patterns and talking about comfort for people and pedestrians. But usually we don't get too deep into temperature and climatic effects with wind tunnels. One thing we can do, sorry, this is a bit of a long answer, but cooling towers. They're big structures on their own, and they can create their own wind flow patterns, so you can get situations where that big plume gets sucked right back into its own air supply. So what it's trying to do is suck in cold air to blow across hot fluids, and that plume that comes out of the cooling tower is warm. So if you suck in the warm, the warm air, what happens is it reduces the efficiency of the cooling. So what you do is you can use the outputs of the wind tunnel model and combine them with climatic information. How warm is it? How cold is it? What temperature is it? What's the humidity? To understand how that's going to work. Or you can look at condensation on a building facade. We can look at what is the plume impact, but then based on the particular climatic condition on that day or that hour, there may or may not be condensation if the plume is warmer or colder than that facade. So there are ways to tie in climate.
Hey guys, we're out of time. Another round of applause for Martin, and thank you very much for a great presentation.
You're very welcome.